So I would like to prove that 0.99999 recurring equals 1. Now at first glance that doesn't appear to be possible. It looks like this number is slightly less than 1. However many 9s you had after that, you would think it's still just slightly less than 1. But I'm going to try and prove that this is actually the case. This is true. And the way we are going to do this is we're going to talk about recurring numbers. What do we mean by recurring? We basically mean these 9s go on forever. So, for example, well, let's do some examples of non-recurring numbers. 1/2 is 0.5. So that's a non-recurring number. 0.5, that's it, full stop. 1/4, 0.25, full stop. 1/8, 0.125. So we're getting more digits, but still, that's it. No more digits after that. But there are numbers where the decimal equivalent carries on, the digits carry on forever. One of the sort of easy ones to think about is 1/3, which equals 0.3333 going on forever, or 0.3 recurring, which you can, by the way, write as 0.3 and you put a dot over the 3. But actually, I think this way is kind of easier to visualize it. Now, and by the way, you can have, it doesn't have to be a single digit that repeats. You can have 1 divided by 11 is 0. So it's 0.90909 going on forever, and you can write that 0.09 and you put a dot over the numbers where the repeat starts and ends. And the other thing that's worth noting is that the repeat doesn't have to start directly after the full stop, after the decimal point I mean. You could have 1/6 equals, oh, I quite like this one, 1/6 is 0.1666666 dot 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 dot. It's important to put the dots there, otherwise it looks like it ends at that point, which if you want to you can write as 0.16 with a dot over the 6. Anyway, that's kind of an aside. I think the 1/3 is more interesting for what we're trying to prove, and I'll tell you why shortly. Oh dear, this pen's a bit. Now the reason I pointed out 1/3, because 1/3 is the same as 3/9. And ninths are interesting because 1/9 is 0.11111 recurring. 2/9 is 0.2222 recurring. 3/9, as we've already set up here, is the same as 1/3, and 1/3 is 0.3333 recurring. And there's a pattern here. 1/9 is 0.1 recurring, 2/9 is 0.2 recurring, 3/9 is 0.3 recurring. And same with 4/9, 5/9, 6/9, 7/9. Let's say 8/9 is 0.8 recurring. And you might say, well, what about 9/9? Or maybe 9/9 is 0.9 recurring. Which indeed it is, but then 9/9 is the same as 1. Now this isn't really what I would call a proof, but it's a way you can start thinking about how these numbers, thinking about recurring numbers is that they go on forever, and when we say forever, we mean forever. You couldn't write out any of these numbers on a piece of paper. You'd run out of paper in the whole universe. You couldn't even store them in a in a computer, you run out of memory. So these numbers really do go on forever. And that's the thing, that's the important thing I think you need to remember about this. Now, even though these numbers go on forever, you can still do maths with them. So for example, let's say for example 3/9 minus 1/9. Well, what does that mean? Well, 3/9 is 0.3333 going on forever, minus 0.11111 going on forever. And you can do this like a sort of traditional subtraction. Now what you can't do is you can't start at the right hand end, because there is no right hand end. Normally when you were subtracting you'd find the right hand end, you go 3 minus 1 is 2, etc. Now we can sort of simulate that here. We can say 3 minus 1 is 2, 3 minus 1 is 2. But you'll just have to sort of imagine that that goes on forever. So 3/9 minus 1/9 is 0.22222, which is 2/9, which is correct. You can also multiply recurring numbers. So let's go back to 1/3 equals 3/9 equals 0.333 recurring. You can multiply that number by 10. So that'd be 10/3. Now let's just do this as a fraction first. 10/3 is the same as 3 1/3. And then if we look at the, so that's just sort of, just note that. And then let's look at the decimal. Now, if you multiply a decimal by 10, what do you do to its digits? You shift them one place to the left. Or you could say you shift the decimal point one place to the right, but let's say you shift the digits one place to the left. So you would have 3.3333 recurring. And this is where I think it starts to get kind of interesting, but also confusing. These 3's after the decimal point go on forever. These 3's after the decimal point go on forever. Even though we've shifted these one step to the left, that doesn't change anything at the sort of right hand edge of this, because there is no right hand edge of this. So you could say we've actually, where has this extra 3 come from? Well, it's come from this infinite series of 3's. Anyway, the point about this is that you can then, okay, well, there's a few interesting things about this. 3 1/3 is 3.33333, and you say, well, that's obvious, isn't it? Because 3 is there, there's the 3, there's the third, the 0.33333. And what, for example, would 10/3, which is 3 1/3, minus 1/3 would be? Well, doing it as the okay, so that the answer is 10/3 minus 1/3 is 9/3, which is 3, and 3 point nothing. But let's do that as a decimal, as a thought experiment. You now can't see the previous page, but let's just imagine instead we're doing 3.33 recurring forever, minus 0.3333 going on forever. Just to show you again, so we're doing 10/3 minus 1/3, 10/3 being 3.3 recurring, 1/3 being 0.3 recurring. Now again, in a normal subtraction you'd find the right hand side and you would try and delete things, but there is no, sorry, you try and take things away, but there is no right hand side. So let's actually do it from the left instead. 3 minus 0 is 3. 3 minus 3 is 0, 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 ... 0 is going on forever, just means they never end, so the answer is 3. And that's fine, you might say. That all adds up, well, or takes away. But the point is, it all seems to make sense because we have said 10^3 minus 1/3 equals 3. And we can see that that is true, because 10^3 minus 1/3 is 9/3, which is 3. Now, going back to our original problem, or our thing we're trying to solve or prove, why does 0.999 equal 1? And when I say I said 0.9999, I meant 0.9999 recurring equal 1. Well, it only works in the recurring version of this. If we said, I mean, for example, 0.9 clearly doesn't equal 1. 0.9999 full stop clearly does not equal 1. 0.99 and then a million more 9s, but then a 9 at the end. So this doesn't go on forever, but it goes on for a very long time, still does not equal 1. But I'm saying that this does equal 1. Well, one way to prove that is to do a bit of mathematical manipulation on it. So, what is 0.999 going on forever, recurring, times 10? Well, when you multiply something by 10, you shift the digits one place to the left, so you have 9.9999 going on forever. So, then what happens if you take that away from that? I'll write it the other way so to make it easier to see. Well, it's like the thing we just did with the 3 1/3. 9 minus 0 is 9. These 9s all come out to zeros. So we end up with 9 exactly. Now, we need to do a little bit of algebra to try and explain what we've just done. Let's use the letter, I don't want to use x because I've been using x's for big multiplication signs, so let's just use y. Let's say y equals 0.9999 recurring. Therefore 10y equals 9.9999 recurring. And we've just shown that 10y minus y equals 9. Just to recap, that's 10y minus 1y is 9 exactly, not 9 point something, not 8 point something, exactly 9, because all the 9s line up and end up being zeros. 10y minus 9 equals 9. Simplify this. 9y equals 9. Divide both sides by 9. Y equals 1. Y equals 1. Y equals 0.999999 recurring. Now it kind of blows your mind. It blows my mind anyway. So I'd like to just try and write something else that proves, or try to help you understand this and why it's important that these 9s go on forever and that these 9s go on forever. If instead we had y equals 0.999 and then ending there, not going on forever, 10y is 9.99, and then it stops there, does not go on forever. 10y minus y is 9.99 minus 0.999. And if we try to do that, so I'm lining up the digits here, do that as a normal subtraction method. I've put the extra 0 because Well, I hope that's obvious why. 0 minus 9 we can't do, so we have to make that 10 minus 9 and change that 9 into an 8. That's not very neat, is it? 10 minus 9 is 1. 8 minus 9 we can't do. Turn that 9 into an 8. Borrow the 1. So we've now got 18 minus 9 is 9. 8 minus 9. And so on. 18 minus 9 is 9. 8 minus 0 is 0. So if I've done that right, in this case, when you're trying to do it with a non-recurring number of 9s, you end up with something that is not a whole number, and that's 9y equals that. If you divide that by 9, and I've done this earlier, so then you say, yes, so therefore what does y equal? Y equals 0.999. If you divide that number by 9, you get 0.999. So the point is that for any, and the same by the way happens if you have 0.99999, a million 9s, but then it ending in a full stop. When you do 10 times that, you shift the digits to the left. The important thing is right at the right hand end, you get this kind of mismatch, where you've got a 9 there and a 0 here. And this is the thing that does not happen when you have 999 recurring. You multiply it by 10, you shift all the digits one place to the left, but these 9s after the decimal point still carry on forever. There is nothing odd that happens at the right hand edge of this, where what used to be a 9 is now a 0, because there is no right hand edge of this. So you've sort of magically created another 9. You could say you've done 10 times y, we've multiplied y by 10, move the digits to the left, but we've got you could think of it as having an extra digit at the end. Now there isn't an end, but that's one way of thinking of it. So going back to this example, it would be as if you said y equals 9.99, y equals 0.999. What happens if we multiply 10? Well, we get 9.999. Now that isn't the case with a non-recurring number, but if it was, if 10 times that was 9.999, then 10y minus y would be 9. It wouldn't be this number, which is not quite 9. I don't know if that helps or hinders, but take it from me. I shouldn't say take it from me, that's the whole point of this video, is try and make you understand yourself. That this is true. You multiply by 10, shift the digit one digit to the left, and you still have the same number of 9s, as in an infinite number of 9s after the decimal point. By the way, you could multiply y by a million, in which case you would move the digit 6 places to the left, and you would have, let's actually write that out. So if y equals 0.9999 recurring forever, 1 million times y is, now I've got to get this right, 99999.9999 going on forever. Even in this case, we've moved this 6 digits. We've moved every digit here 6 digits to the left. There are still the same number of 9s after the decimal point in this number as there are in this number. They go up because they go on forever. So I suppose you could even do, what's a million y minus 1y? Well, it's 99999.9999 going on forever minus 0.9999 going on forever, which is 99999.0. and that is 9999999 So 999999y equals 999999, therefore y equals 1. And that's the magic, that's not really the right word, that's the special properties of recurring numbers and why they don't quite act like you might think they do. There we go.